the Shannon information doesn't tell you about the meaning, right?
Mm.
There's certain issues there. But one thing that did stick out to me about this paper, I believe it was in this paper that you said, if we think about these light cones, that expanding the horizon is what enables Shannon information to acquire meaning because data becomes causally linked to distant and past experiences and acquires implications for future expectations. So, can you help like decouple that a little bit?
Yeah, yeah, and that sounds like I'm almost positive that one was from that's a
Paper.
Chris Fields sentence, and
Oh, my
that one
bad.
was I'm almost positive, and that
Yeah.
one was from a paper that Chris and I did on meaning and where meaning comes from. And
Oh, okay.
and you should have him on too. Chris is also absolutely remarkable. So
Yeah, I've come across his research before. Yeah, he's great.
yeah, you should definitely talk to him. But uh the what I think is critical there, and what Chris and I have been working on a lot is the centrality of this concept of the observer.
Mm,
And it's this idea that, and I actually think that's one of the things Shannon information gets right, in that it doesn't assume that meaning is I mean, yes, it misses out on meaning, but when you're trying to capture meaning, you start to get this idea like, well, there is one meaning and it's our job to kind of discover it. And I think a better frame is that there are multiple observers which have to imbue data with meaning. It's on them to interpret it, and it means different things to different observers. Everything is observer relative. And in fact, I don't know if you've seen this paper, but there's a really cool recent there's a really cool piece of research by Josh Bongard, one of my collaborators, and his student Tusa, on polycomputation. And then Josh and I wrote a review of and some new ideas about this concept of polycomputing, and this idea that one way to squeeze more computational power out of a piece of biology, or in fact out of anything, is not to change the thing, but to change your perspective as an observer, in the sense that multiple
mm,
observers can be looking at the exact same physical process and get different computational results out of it, depending on what their perspective is and what their interpretation is. So it's this, and it's got this, it's an idea that has this weird match to, some ideas in kind of psychology and so on, that changing your perspective on things is a tool that you have in addition to actually trying to change the thing itself. And so that's part of it, is that we have to think about that meaning is very much relative to some observer, which, by the way, might be the system itself. An observer doesn't mean that there's not always some sort of external thing that is there to give something meaning. The system itself can be it's like this strange loop, as Hofstadter puts it, that can do that for itself if it's a complex enough system.
this light cone idea, and I think this brings in something you've said about cancer cells, or at least
Mm.
your
Yeah.
theory of how cancer cells look, that they
Yeah.
have like sort of the wrong scope of what they themselves are.
Yeah.
Can you explain that a little bit?
Sure.
Yeah.
Well, so a lot of cancer research focuses on why do we get cancer, right? Like what causes it? And I think that the right way, or a better way, to think about the kind of the origin of it is, why is there ever anything but cancer? Why isn't it all
Mm-hmm.
cancer all the time? Because
Right.
if you think about individual cells as which are as our ancestors, their basic state is not to sit quietly as a disposable organ somewhere. Their basic state is to reproduce and go where life is good. We are made of pieces that want to behave like a tumor. They want to go wherever they want. They want to reproduce as much as they possibly can. They want to hijack other cells around them to help them do whatever they need to do. That's the basic state. The real mystery is what keeps that under control. And I think this was well recognized by people kind of at the dawn of the developmental and cell biology, but it sort of lost steam for a while. But it's a very powerful idea, because then you ask yourself, well, if we really take this cognitive light cone thing seriously, we look at individual cells and we say, so what's happening here is that there are a variety of signals, and those may involve the stuff that we've been talking about, so gap junction, stress propagation, with all kinds of other things. What they're doing is they're partially erasing the identity of these individual cells to enable the collective to work towards a very large goal, like making a nice liver or a kidney or whatever. And then you start to think through, well, what would a failure mode look like? So you get some sort of oncogene that let's say shuts down all the gap junctional communication for that cell. And immediately what happens is once that cell is electrically isolated from its neighbors, it can now start to have an individual identity. And that leads to a calculus of individual little tiny cell goals. And that cell can now, as far as that cell is concerned now, the rest of the body is just external environment. So what happens with these electrical networks, and of course chemical and biomechanical networks, is that they set the boundary between a cell and the outside world. If you're a cell and you're connected to a whole bunch of other cells, the boundary of yourself is huge. It might be the whole body, and then everything else is sort of external environment. But as soon as that gap junction breaks, your self is now tiny. It's just a single cell. So that boundary between self and world grows and shrinks. It grows during development and grows during evolutionary, the course of evolution, and then it shrinks during cancer, where, and that's really important to think about, that these cancer cells are not any more selfish than normal cells. In a lot of game theory, you treat the cells as more selfish. They're not more selfish. They're exactly as selfish as every cell. They just have a tiny little self. So all the other cells are also being incredibly selfish, but their self is huge. And so they're all working towards this common purpose that we see of as an organ, or in fact, the whole organism. But it's not because they're not selfish. It's because their identity is partially erased through their tight informational linkage to other cells. And so cancer is exactly what you would expect from a breakdown of that process. As soon as you're disconnected, and we see as soon as you get a strong oncogene, the first thing that happens is it shuts down gap junctional communication. You get a weird voltage, as a depolarized voltage state. And then you start doing this calculus. Well, where am I better off? Well, I'm going to go down there, and then I'm going to proliferate as much as I want. And this is metastasis. And then your goals start to deviate from the goals of the rest of the collective.
Yeah, I love that you said, you pointed out the cancer cell is no more selfish than another cell. It just has the wrong scope of what it is, kind of. It doesn't have the proper. Its light cone is deformed, let's say, but
and it's shrunk, and the key is, again, so to make good on this promise at the beginning that this wasn't going to be just philosophy, what we've been able to do is to take that weird way of thinking about it and turn it into a therapeutic strategy. So once you start thinking about that, we think, okay, so maybe we don't need to kill the cells, and maybe the problem isn't the molecular hardware. Maybe what we can do is physiologically reconnect it to the network, and it should go back to doing its normal thing. And that's in fact what we've done. So we have a whole body of work on cancer in the frog model, and we're now moving to glioblastoma in human cells. Is to convert the cell with a really strong, nasty oncogene like a KRAS mutation, force it to be in proper electrical state with its neighbors, and the cell they normalize. There's no tumor. They go, even though the oncogene is blazingly strongly expressed, they just go back to doing what they normally do, because they're now, again, they're part of this morphogenetic collective.
Will we eventually, you think, be able to electrically communicate with, say, a cancer cell and just change the information going into the cell via, say, electrical currents, and tell it to do something else? Like, is that a decent explanation of where we're going towards, or is it a little different than that?
It's reasonable, but I'll twist that just a little bit. Here's where I think it's going. Down at the lower level. So if you zoom in, yes, I think that's what we're looking at is aberrant electrical and other kinds of signaling between cells. That's the target. However, I don't think that the way that we're going to be manipulating this is by focusing our intervention efforts directly at that layer. And the reason I don't think that's what we're going to do, and I'll tell you what I do think we're going to do, is that it's kind of like programming a computer. The way you programmed a computer in the 40s and 50s is you had to physically interact with the hardware. You literally had to sit there and rewire it, right? And that's what all of modern molecular medicine is about. It's a CRISPR and genomic editing and rewiring pathways and protein engineering. Like, all that stuff is down at the level of the hardware. I think what the information technology revolution has taught us is that if your hardware is good enough, and I think the biological hardware is definitely good enough to do this, the better way to do this is to communicate with the system using its own built-in interface, not to try to rewire it, but to reset the set point and take advantage of its built-in competencies. So reprogrammability. So what I think we're going to be doing is, I don't think we're going to be telling every cell what to do in either cancer or regenerative medicine context. What I think we're going to be doing is basically a rough way of saying is retraining it. We're going to be using high level stimuli, and I think it's AI. Recent examples of AI and various techniques in machine learning show great promise in being that translation layer to do very high level top down interventions where the details are all handled by the system itself. This is how we've done a lot of our work on bioelectrics. We can make cells, we can make bodies form an eye in weird locations, or an extra leg, or repair various structures. And it's never by telling the individual cells what to do. It's never by differentiating stem cells. It's always by communicating with a collective intelligence with a fairly simple signal. Looks like a subroutine call that just says, build an eye here, or regrow whatever normally goes here. That's the kind of stuff. You don't want to be down at the level. I say this to my students. You don't get out your soldering iron every time you want to go from Photoshop to Microsoft Word, right? I mean, you could, but
Right.
but we don't do that. Why don't we do that? Because your system has a much better way where you can take advantage of these built-in multi-scale controls, and that's what I think we're going to be doing. There's actually a really interesting piece of this that ties into some medical issues that have been coming up for years. We just had a talk by Fabrizio Benedetti, who's this amazing placebo researcher, and he has this quote which I just love, and I'm now using it all over the place, which is he said, drugs and words have the same mechanism of action. And he's exactly right. By looking at how bodies respond to the context of being given a specific drug or being given a placebo, whether the doctor was wearing a white lab coat or wasn't, or whether he told you were getting a drug, or whether he told you were getting the best drug, or what, all of those things have massive implications for the therapeutic outcome. And that's because we are part of this multi-scale system where high-level cognitive expectations of what's going to happen filter down to the molecular details of how your cells actually react. And this is what makes hypnodermatology work. It's what makes the placebo effect work. And it's also, lest people think that this is some like weird exotic effect, that's how you get up out of bed in the morning. Because when you're laying there and you decide to stand up out of bed, what's happening is that high-level executive cognitive function that says, you know what, I think I'm going to get up out of bed now, has to traverse down to change the molecular properties of your muscles, of the cell membrane in your muscles. In order for you to take these voluntary actions, that cognitive intent has to change the way your voltage is spread across the cell membrane. It has to affect the micro level physiology. So this business where top level cognitive states affect molecular biology is not some weird, mind brain medicine woo woo stuff. It's the daily reality of being a behaving living multi-scale agent that uses bioelectricity mostly, but also a bunch of other stuff to cross levels like that, to go from cognitive goals to molecular states.